Of the Alumni Meet and New Year 2014 of Presidency University Physics Department. Our Honorable Vice Chancellor, Professor Anuradha Dutta, Professor Shomak Rai Choudhury, Head of the Department of Physics and Dean of Natural and Mathematical Sciences, Professor Shobboshachi Bhattacharya, Distinguished ATC Post Professor of Presidency University, Professor Shubhanshu Shekhar Manna of S.N. Bose National Center for Basic Sciences, many distinguished alumni of the Department of Physics, and dear students of the University of Physics and other departments, and other students from other institutions from many local areas, schools, colleges and universities. It gives me great pleasure to welcome you to this inaugural session of our alumni meet and reunion. Without further ado, I call upon the Presidency Physics Choir, which has been formed, so their maiden performance for this occasion, to come upon and present the inaugural song. Thank you. I would like to now invite our Honorable Vice Chancellor, Professor Anuradha Lohia, to please come on the stage. I would now invite Professor Shomok Raichaudhuri, Head of the Department of Physics and Dean of Natural and Mathematical Sciences of Presidency University, on the dais. I would now call upon Professor Sabyasachi Bhattacharya, the distinguished AJC Bose Professor of Presidency University, to come to the dais. Finally, I would call Professor Shubhranshu Shekhar Manna of S.N. Bose National Center for Basic Sciences to come on the dais. I would now invite our Honorable Vice Chancellor, Professor Anuradha Lohia, to address this gathering.
Good afternoon. A very, very warm welcome to all of you. I know you were all in the physics department, but I do feel that you're all presidentials who've come together. And I wish this was a reunion of my batch, not just physics department. I'm almost feeling envious. I cannot tell you how overwhelming it is for me to see all of you together in this auditorium. I know you're all going to share lots of memories, have a great time together, and take back more memories which you'll create in the next 2 days, and which we will share till the next reunion when you meet again. I also find it very overwhelming when people keep on introducing me as the Honorable Vice Chancellor. I don't know if I deserve all 3 words or not. I joined presidency in 1972, and like most of us, had a lot of fun. I did have physics as my pass course, and I remember more fun in the physics pass course than actually physics, which was very difficult. And I studied physiology, and we all were in awe of everyone who studied physics because we knew you were the smartest. And we were those poor leftovers in the science section who joined physiology. So it's really quite incredible that I address today all the senior physicists who were before me in this university, some after me as well, but all of you were the cream and the elite of the science subjects that you were in physics. Today, I think later in the afternoon, we are going to have a session on the role of the university in education today in West Bengal. Before we come to that, I'd just like to share a few thoughts with you so that we may discuss it further in the panel discussion. We've been left with the onerous task of recreating Presidency College to Presidency University. Presidency College was not just a concept, it was such a huge institution which permeated each of our beings. We carried it with us. Once you entered the portals of Presidency College, everyone carried it in their persona. We are Presidency College. And for many years I remember the first time we were, at least I remember I was part of a protest, was when they started transferring our wonderful teachers to other colleges. That was the first time in about 1979 or 80, somewhere around that time. Before that, professors of Presidency College were again those hallowed human beings who were institutions in themselves. And then the government took a policy of sharing them with other colleges, maybe rightly so, but not for presidentials. We were not going to share. Following that, there was a lot of talk and a lot of sustained effort, which finally led to the formation of the university of our beloved college. On paper, it sounds wonderful. Yes, we are finally Presidency University. It also sounded great till I was appointed Vice Chancellor. But you know, in the last 6 months, I'm beginning to see how tough it is. What expectations that everyone holds. What should be Presidency University? First of all, to continue the tradition of Presidency College is hard enough. It's hard enough because of social changes. It's hard enough because of perceptions. It's hard enough because we have changed. What we expect of our future generations has changed. I don't think my parents or anybody's parents thought too much about what we were going to do once we entered and left Presidency College. But today already there are preconceived notions. And then of course there's the problem of university. When I was offered this position in late April this year, many of my batchmates and colleagues rang up and said, Presidency কিন্তু জানিস তো undergraduate teaching এর জন্য সবথেকে বেশি বিখ্যাত। তুই একটা জিনিস করবি যেন undergraduate teaching টা নষ্ট না হয়। I thought, why are they telling me this? নষ্ট হবে কেন? তারপরে আরো কয়েকজন ফোন করে বলল, এবারে কিন্তু ইউনিভার্সিটি হয়ে গেছে, দেখিস যেন রিসার্চটা ভালো করে হয়। Fair enough. আচ্ছা তুই প্রোগ্রামটা কি করবি? মানে সেই ক্লাসরুম বেসড টিচিং হবে নাকি আমাদের এবারে লিবারাল আর্টস এন্ড সায়েন্সেস হবে? Good question. I just kept getting questioned. And for the first 3 months, I was barraged with question after question, which really made me sit back and think. Coupled with these questions, which are all very, every one of them had the love and the aspiration of each presidential, and the well-wishers who really wanted us to be that premier institute, not just in Bengal or India, but you know, we really equate ourselves to the best of the very best in the world. How do I fulfill this? How do I take this forward? You know, I've been very lucky. I had a wonderful predecessor, Professor Malavika Sarkar, who was also a presidential, and she started building it brick by brick as a university. So when this job was handed over to me, the statutes were almost completed, the rules were in place. Some infrastructure had started to get along. More importantly, she had already recruited 130 faculty. Okay, so the first step was pretty good. Now comes harder steps. Our faculty sanction strength is 300. And if we wish to have a healthy student-faculty ratio, this is going to be somewhere very difficult to contain. Everyone wants a seat in Presidency College. The first andolan I faced from the students within weeks of joining was, seat বাড়ানো হচ্ছে না কেন? না, আমরা কেন MSc পড়তে পারবো না এখানে? Right request, wrong person, wrong attributes. We have to follow rules. Just now, Ujjwala also told me a complaint about some rule that I followed. It's pretty tough, you know, to walk this tightrope between what we want, what we can actually do, where is the balance, and what is that very delicate road that a Vice Chancellor must forge ahead with, or at least the Vice Chancellor is happy, if not her colleagues. It's very hard. I don't pat myself on the back when I tell you I haven't really slept in 6 months. What I really want to know, and today I ask each of you sitting in front of me, help me. Tell me where to take our university. Give me your suggestions. Give me your complaints. Also show me the road. And more importantly, I request you to come and participate. I wish you'll come and teach. Those of you who are still interested are in the profession. I know Ashok is sitting here somewhere, and there are others amongst you who are still involved with physics. Please help me rebuild our heritage and handhold me. I really was never prepared for a job like this. My colleague from Bose Institute is sitting here, Pradeep Parekh, and I think they all stared at me when they heard that I had accepted this job. I really must have been the most unlikely person to sit in this chair. But once I have accepted the challenge, I'm going to make sure that I live up to being a presidential. And I can't do it alone. Each of you have to help me. And I request you today to give me your best and your best suggestions and your worst complaints. I'm here for taking care of both of them. But don't just be bystanders, be a part of presidency. And let's take this together. I hope you all have a gala time today and tomorrow, and I wish you all the best. I cannot tell you how happy I am that Shomuk is our dean and our head of the Department of Physics, because he really comes up and talks to me about every single thing, challenges me, and we argue all the time, and it's wonderful. I feel alive. And thankfully, Shorbusha has joined. He comes with his benevolence, with his quiet seriousness and gratitude, and very gently shows the way ahead. So with these two at my side, I almost feel like I'm a part of physics. Of course, all of us are presidentials. But let it not stop at Shomuk and Shorbusha, inviting all of you to be part of that wonderful adventure once again, that is presidency. Thank you all.
Let us thank Professor Lohia for her speech. Now I call upon Professor Shomuk Raichaudhuri to talk to the gathering.
Welcome to everybody. I will be brief. I would like to continue what Professor Lohia, our Honorable Vice Chancellor, started by saying. And in particular, I'd also like to point out that what you see in this auditorium right now is kind of a microcosm of what we intend our university and our physics department, in which direction we intend to take them to. Here you see the first half of this auditorium are people who have walked these corridors and have been through presidency and have ended up in varying degrees in various places, in various walks of life. And at the back, the second half of the auditorium, we have invited students from high schools and colleges and universities from all over Calcutta to come and witness what we're doing here in the academic sessions we have in the first half of the 2 days. The people here who have been the past of presidency, the present of presidency, and I hope we have at the back of the auditorium some of the future of presidency. Where we, I think, in this transformation of college to university, we stand at a crossroads. Here are people who most of you here who've come for the reunion, are like me. We are at the locus of the most important and probably the most enjoyable days of our lives. And we look back and think, why? What made presidency this magical place, this phenomenon that has actually permeated into every part of our lives? And when I emailed you, a lot of you probably got the email directly, the first email that went out inviting you to come to this event. I'm here talking to the alumni. I said we would like to come together, and as Professor Lohia said, at this moment where we are witnessing a transformation from college to university, we come together and share our views, wisdom, our experiences in trying to figure out where we want to go from here. The brick by brick analogy is actually very apt for us, because in this transformation from probably the strongest undergraduate college in India, certainly in the sciences, certainly in physics, to a research active university is not going to be easy, hasn't been easy for us. We are aiming to become what the Americans call an R1 university, where each faculty member will spend half their time in research and half their time teaching, and we do not want our whole legacy of good teaching, good undergraduate teaching, to disintegrate in the process. We want to keep that up. Now, it's easier for the physics department because even in the days of being an undergraduate, college presidency was always very research active. If you look at the 50s, the 60s, the 70s, some of the sterling research was done in presidency, not just in the theoretical sciences, but some of the experimental labs in presidency physics were absolutely fantastic, and there are people here who witnessed all that. I mean, when I came in as a student in 1980, much of that had gone, but we still had Professor Amar Rayachudhuri, Professor Shyamal Sengupta, who were very, very research active in the theoretical sciences. And then, of course, the teaching tradition of the university did continue, but the research tradition often didn't. And we have to transform all that and make it into one of the prime universities, not just of India, but of the world. I will talk about this a little more towards the end of the day. But what I want to say is that bringing all of you, the alumni here, together with the present students of the university, the present faculty of the university, and hopefully the future of the university together, is because current students, not just the students of presidency, but younger folk who study in schools, like the ones who are sitting down in the back, need the confidence in our present education system. They need to be shown that if you study in a college like presidency, a university like presidency, you study physics, you can succeed in life. And you can end up not just teaching physics at a college or a university or do research, but you can do anything. If I take a census of the professions of our alumni from left to right here, we will find that we have ended up in every single part of the world and every single profession you can think of. People come up to, young people come up to me and say, what's the use in studying physics? What's the use in not studying engineering or medicine? What is the use of even coming to presidency? And I would like to say to them that to prepare somebody to be a whole rounded human being so that they can take on the world in any profession possible, there is nothing like the education we now give at presidency, and of course in the presidency that we are dreaming to build. And this is, I think, probably the most the prominent reason for us to get together, to give our students and future students the confidence that going through a university like presidency can build the citizens of the future. Thank you very much for coming. A very warm welcome to you, and I hope you meet old friends here, and I would like to meet every single one of you, and let us see this as a beginning of a relationship between the old students of the college and the new dreams of the university. Thank you very much.
A souvenir has been published on the occasion of this alumni meet and reunion, and we now propose to officially inaugurate the souvenir. And somebody is coming with one copy of the souvenir, and Shubhranshu Shekhar Manna is the chief editor of the souvenir, and he and Professor Lohia together officially inaugurate this souvenir. This would be available for all the registered alumni. There will be a distribution at the tea session. I will announce it later. Now, the other three people seated, they will also get copies of this souvenir. We have come to the end of the inaugural session, and we would start the first of the public. There are few, although it's a reunion and alumni meet, we have kept some public events that anybody can attend. And the next, okay, let's I think the distinguished guests can now we have organized, as I said, a few events in connection with the reunion that can also be attended by the members of the general public. And the first of this event we are starting now. Over the course of the 2 days, we have organized a set of public lectures on topics in physics which are at the frontiers of current research, and which are delivered by very distinguished alumni who are at the forefront of this research. And we have organized it into 2 different sessions, one today and one tomorrow. And although it may seem there, so two lectures today, which will start right now, and 2 other lectures tomorrow. They may seem different, but actually all these 4 lectures are concerned with broken symmetries in nature, and how they're broken, their modes, and actually it has very tremendous effect on our daily life, our existence. So for the first session would be chaired by Professor Sabyasachi Bhattacharya, and he will introduce the speakers and the session. So this session will be conducted by him. He is the chair of this first public lecture event.
Thank you. Good afternoon, everyone, and welcome to this first academic session of the program. I wish to extend a very special welcome to those of you who have come from outside of this institution and from other institutions around this city and the state, and I hope that you will continue to come to these programs of ours. My name, as you have heard, is Sabyasachi Bhattacharya, and I am chairing the session because the person who was supposed to was unable to do so, but my friends suspect a conspiracy in my doing this, and that's because the reunions are also the occasions where inter-class rivalries are sometimes spoken of, and in this particular session, the 2 speakers were both my classmates and have been my very close friends for all these years. So I thought I'll make a few personal remarks in the spirit of what I just said. So I think that statistics says that my class, my presidency class, holds the record for maximum number of graduates who stayed in physics for their entire professional career. This afternoon, we will also hear from those distinguished alumni who have gone to excel in other parts of society, other kind of careers. But this session is for physics. So, my class having this peculiar record is undoubtedly a collective phenomenon. Among those of us who went through a very turbulent time in the history of presidency and of the state. And I wonder if this extraordinary loyalty that my class has had to an academic career in physics was not only in spite of the difficulties, but perhaps because of it. And it gave rise to a stubbornness amongst us that we shall move ahead and we shall not be denied, come what may. And so it is especially gratifying to me and to my peers over these turbulent years that after a very, very long time, nearly half a century later, we are back here in presidency doing exactly what we then dreamt that we should do someday. Dreams rarely come true, And therefore, on behalf of all my friends and my fellow students then, I express our gratitude and thanks to Presidency. Thank you indeed. Now, let me just elaborate a little bit about what this lecture is supposed to achieve. So the public lectures are going to be part of the academic programs for the next 2 years. On each day, we will have 2 speakers in each program. One, a theoretician, and the other, an experimentalist, in what we have decided to call a Jugalbandi. And they will speak on a common subject of great current interest and will complement each other in revealing to all of you, those who are veterans and those of you who are aspirants to becoming veterans one day like us, that it will reveal to all of you the full range of work, experimental and theoretical, that happens at the frontier of physics, and will provide the audience with a view, although in a simpler, more accessible format, the essence of how progress is really made in physics. We have also tried to keep some conceptual connection or overlap between today's program, which is on broken symmetry and new phases, and tomorrow's program, which is called Higgs. And what those linkages are, I am not going to tell you. In order to know that, you will have to attend tomorrow's program as well. Now, the title of today's program here is Broken Symmetries and Novel Phases of Matter. There is a summary abstract on the website, and I will not repeat it. I will only introduce the speakers. I told you that both were my classmates here in Presidency, and these 2 were special even in that very special class. I, for one, learned as much from them as I did from my teachers and from our textbooks. Many of us went to Delhi to do our masters, and these 2 were the toppers in our MSc class in Delhi, which we took as a collective indication of the adventurous steps we had taken in search of our education in those difficult times. I am thankful for both of them to have traveled here to deliver these lectures. Thank you very, very much. Now, I will begin with the first speaker, and after his talk, I will introduce the second speaker. The first speaker is Professor Chandan Dasgupta, who is now at the Indian Institute of Science. But since this is his alma mater, I thought I would begin from the very beginning. He came to our class from Taki Government High School. After his BSc here and his MSc in Delhi, he received his PhD with Professor Brooks Harris in statistical physics at the University of Pennsylvania, where his name still hangs on the walls of the department as the top student of his class. Afterwards, he did postdoctoral work with Sheng Ma at University of California in San Diego. Many of you physicists, professors, would have remembered him from his textbook on critical phenomena. And then with the legendary Professor Bert Halperin at Harvard. Following this, he spent a few years at the University of Minnesota as a member of the faculty. Subsequently, he joined the Indian Institute of Science during a very special period when the IISc Physics Department was able to attract a fair number of outstanding stars from all over the world and became a powerhouse in condensed matter physics in general. And Chandan was among that very select group. Today, he is also the Dean of the Undergraduate Studies at IISc, and I mention this in particular because they have started an undergraduate program with the science at IISc. It's a watershed event in India's higher education, and he's at the helm of what is now on everybody's radar in the country. Now I request Chandan to come up here and begin the Jugalbandi. Ladies and gentlemen, Chandan Dasgupta.
Okay, sorry for a few minutes being taken to get everything ready. Meanwhile, let me begin by thanking the organizers of this wonderful union for organizing it, and also, of course, for an invitation to attend it and to give a talk here. See, about more than 40 years ago, I spent 3 years, actually little more than 3 years, because we are significantly in those days, so more than 3 years here. Those were really wonderful years of my life. Learned a great deal during that period, made wonderful friends, and all these things have really helped me a lot throughout these 40 odd years. So it's great to see that, and again, I hope, wish all the best for Distance University to proceed in the direction that it is planning to do, all that, and whatever help we can provide, do so. So now, shall I start? Talk? Have you all done it? Yeah? Okay, and also thanks Shobho for the wonderful introduction, and also for giving us this opportunity, myself and also the next speaker, Professor Gulab Dakhtar. I think he mentioned that we were lab partners for not just 3 years here, but also the 2 years we spent in Delhi University. 5 years we were lab partners. So it is wonderful to be, after so many years, to be back and giving talks in the same session. So again, thanks for that. So today, as I understand, it's a very general audience, so I have prepared a very general talk on phase transitions and spontaneous breaking of symmetry. Basically, I'll try to keep things at a very non-technical level, so that it's accessible to most of the people. Of course, I mean, there are experts who know much more about this than I do, and I basically apologize to them that it's very sort of elementary to them, but it's not meant for experts, it's meant for a lot of people sitting at the back have come from school, so I hope it will be accessible. So this is, we start with basically outline, nothing much. I'll take about 5 minutes to give an introduction to the kind of physics that I do. Since quantum matter physics is my area, and we'll try to give a, say something about why it is interesting, why people are interested in it. And then we'll specialize in some parts of quantum matter physics, phase transitions, and we'll give some examples from real life, which will make this phenomenon common to the people who are not physicists. And then we'll discuss the second aspect, which is very important in the discussion of phase transitions, which is mainly continuous breaking of symmetries. Depends on how much time all these things take. We'll have, if there is time, then we'll talk about conductivity. Conductive phase transition, one of the most important examples of phase transitions, and specifically because I have done some work, we have done some work in the area, but I don't know how much time we will have for that. So this is my area of work is condensed matter physics. I do theoretical work in this area, and just spend a couple of slides on what is it that people call condensed matter physics, why it's interesting, why it's important, and so on. So I see 40 years ago, more than 45 years ago, when we were doing our BSc here at this college, there was a subject called properties of matter. And what we call condensed matter physics these days actually is basically a development of that into many other things, which I'll try to just give you some ideas about. So here, what we're interested in is we're interested in some collective properties of systems where you have a large number of what I call quote-unquote objects which interact with each other. And what we're interested in is basically some cases equilibrium properties, in some cases non-equilibrium properties, whatever. What properties we're interested in, that depends of course on the specific question that one is asking. But the systems are basically consisting of a very large number of objects which interact with each other. And these are some examples. Originally, when we, this used to be called solid state physics, when we were primarily interested in electrons and ions, which are there in the solid. Again, one is talking about liquid crystals, then we'll be talking about atoms and molecules, then I talking about objects. But then these days, there are many applications of this quantum matter physics to areas where the basic interacting objects are mesoscopic, like colloidal spheres or polymers. They could be even macroscopic, like there are a lot of interest in granular materials, the characteristic properties of sand dunes and things like that, foams, etc. And these days, people are also developing models for understanding the collective behavior of living now encompasses systems which fall obvious categories. And when you talk about interactions, it basically means that they are not, these objects are not behaving independently. The behavior of one of them is influenced by the behavior of some other object. That's why they interact. And large numbers, theoretically one assumes what is known as thermodynamic limit, but the number of particles goes to infinity. But in reality, of course, nothing is infinity. And these days, computer simulations are playing an important role in understanding many quantum matter systems. So in those cases, one is talking about maybe billion objects interacting with each other. And so studies of all these things generally now go under the name of quantum matter physics. And the basic disciplines of physics which are important in this context are statistical physics, both equilibrium and non-equilibrium. Many-body theory, when quantum effects are important, then usually use that area is called many-body theory. And then to try to study dynamics, theory of dynamical systems also plays a very important role. This is a general area. And then, of course, one may ask, why so many people are interested in it? There are, of course, many practical applications. One of the things that drive research in this way, in this direction, specifically materials, the development of new materials which are of use in many different contexts. From the theoretical point of view, the interest comes because basically when you have a collection of interacting objects, then that sometimes leads to collective phenomena which in some sense is very different, difficult to guess, just by looking at individual objects or just two objects, how they're interacting with each other. So this is in some sense a line of thinking that has been promoted by Dr. Bill Anderson, one of the most influential physicists over the last 100 years. He's now 90 and still going strong. Many years ago, he wrote an article in this Science magazine, and which was called "More is Different." And that has, to some extent, become a slogan, so to speak, for people who deal with this kind of systems. And the basic idea here is this, that many new physical effects can arise when you have a very large number of objects interacting with each other. And this is a collective behavior. One can see things that are interesting, that are useful, and that one just simply cannot guess by looking at one or two particles and how they're interacting. So these collective properties of system of interacting particles is what basically is theoretically driving this field. And many new phenomena, many new effects, many new applications that arise because of that. And this phase transition, which is going to be the subject of my talk today, is one example. That this is an example of a collective behavior that is arising because one has a very large number of particles in a system which are interacting with each other. So this brings me to the first topic, which is phase transitions. And all of you more or less know what phase transitions are all about. In the sense that all of you know that a particular material can, depending on the external conditions, can exist in different phases, different states, which have very different properties. And as one changes some external parameter like temperature or pressure or magnetic systems, magnetic field, the system actually goes from one such phase to another, and as a result, there is a qualitative change in the thermodynamic behavior of the system. So these are special points or lines or whatever in the parameter space across which the system changes from one of these phases to another phase. And the most familiar example of this phase transformation is something that you are all familiar with in everyday life, which is basically most substances that you are familiar with can exist in three different phases at very high temperatures, temperature and pressure. High temperature, low pressure system typically is the gas phase. Then at very low temperatures and high pressure, one of these cases is solid, and intermediate cases one is the liquid. So these are the three different phases that a particular material can have. And as one goes across one of these lines, there is a transition from one of these phases to another. So the property of the system changes. As for example, the most familiar example is of course that of water. This is shown in the next picture. So we know 1 atmosphere pressure, this is temperature. So as one 0 degrees temperature in Celsius, then there is a transition, 0 degrees Celsius, there is a transition from ice to water, ice melts. and then 100 degrees there is a transition from water to steam. The water boils and it has a transformation to the gas. So these are the three phases that this material, the water, can have. And by varying temperature, pressure, etc., one can go from one phase to another. And these are examples of phase transition. And these are the kind of things. I mean, there are many such examples where similar things happen, and we'll be discussing the behavior near to phase transition and so on. Now, there are a few things that you can already see from this picture. We have drawn this line here, water, and on this side is the gas, water vapor. This line somehow ends at this particular point. And this point is very important. It's called a critical point, and we'll come back to that later on. Where this other line, for example, which is between ice and water, that continues, doesn't end at a critical point. The reason that happens is something that we will discuss as we go along. But you see that the nature of the transition, of course, depends on exactly where one is crossing this boundary. For example, when ice melts into water, you know that there is a latent heat, which in thermodynamics basically means that the entropy of water is different from the entropy of ice, and latent heat basically is the difference between the two entropies. So there is a discontinuous change in the entropy as one goes across the time. Same thing happens when one boils water. So there is a discontinuous change across these lines. But there are other situations where we'll see that as one goes across a phase boundary, the change is not discontinuous. Everything changes continuously. So basically, I talk about two different kinds of phase transitions. One is called the first order phase transition, where the volume, entropy, etc., which are first derivatives of a free energy. This is again something for people who are thermodynamics. These things change discontinuously across the transition. So I mean, again, going back to this picture where you have solid, liquid, and gas, the solid liquid transition typically is of this kind. That, so as you know, density of water is different to the density of ice, there is latent heat and so on and so forth. So both the volume and the entropy are changing discontinuously across this transition. But I pointed out this point, special point, and if I now look at the behavior here, the special point, we'll see that this behavior is somewhat different in the following sense. Now, if I look at the transition between the liquid and the gas, again, typically around here, this transition will be first order. There is a latent heat of boiling, and of course the density of water vapor is quite different from the density of liquid water. But as one actually goes along this line, and after this critical point, this discontinuity is becoming smaller and smaller. In the sense, the difference between the density of, let's say, liquid water and steam will become smaller and smaller as one goes along this line. And eventually, at this point, this difference basically disappears. And this point is special, it's called a critical point. And it basically means that at this critical point, there are no discontinuous changes in the entropy or density and things like that. And then one has a different kind of the phase transition, which we'll call a continuous phase transition for obvious reasons, that here the discontinuity has gone to 0. So the behavior that one sees is first order phase transition, and the behavior that one finds at this critical points, continuous phase transitions, are actually very different. And I'll try to sort of give you some illustrations as to how these things are different. What happens at this first order phase transitions is that there is something called metastability, which leads to super heating, super cooling, and things like that, which is explained in the following way. So let's just look at a point in this phase boundary. At this point, on the left of this point, we have a solid, the right of this point is the liquid. At that point itself, on the phase boundary, both the solid and the liquid are equally stable. So it's called the coexistence point or coexistence line. Now, if you go a little bit away from that point, again, the solid doesn't lose its stability, the liquid doesn't lose its stability. What happens is that the relative free energies of the two phases change. On this line, the free energy is the same. On the left-hand side, solid has a lot of free energy. On the right, liquid has a lot of free energy. But both these phases are locally stable, very close to this phase boundary, which leads to metastability and superheating and supercooling, for example. We start with the liquid, and if I continue to cool it, one can go beyond this line. The system can still be in the liquid state, but that will be a metastable liquid state. And if you make a disturbance in that system, it will transform itself to a more stable solid phase. So this this is the kind of behavior that one sees near first order phase transitions. Second order phase transitions, continuous phase transitions, this kind of behavior doesn't appear because again, the two phases are not really distinct right at the critical point. And what happens instead is that there are large fluctuations. That thermodynamics, of course, there are averages and then there are fluctuations about averages. If you look at the internal energy, that's one quantity. But if you look at the fluctuations of the internal energy, then I get a specific heat, which is another thermodynamic quantity. So these fluctuations become very, very large near critical points. And this was actually theoretically a very important and very difficult problem. And only in the 80s, actually late 70s, Kate Wilson developed a framework known as renormalization group framework, scaling framework, in which one could begin to understand what exactly is happening near these critical points. So, as you can see, this is an old problem, recently solved to some extent. And phase transitions, they have very different behavior depending on whether one is talking about a first order transition or the continuous phase transition. There's one more thing about this critical point that I want to point out, that for example, one can start here, where it was the gas stage, and then go around this critical point to that point, where it wants to be the liquid. So one can go from the gas to the liquid without encountering any phase boundary. And this eventually we will see is related to symmetry. This is possible because the gas and the liquid have the same symmetry, whereas it doesn't happen for the solid to liquid transition because the symmetry of this phases are different. One cannot go between the solid back and forth between the solid and the liquid without crossing a phase. Now there are students, etc. So I thought maybe show a few videos which illustrate some of this. Some of these things that I just told you. So one thing I told you about is that the liquid to solid transition is first order, and near the transition there is supercooling or superheating, metastability. And if one supercools, for example, into a state which is only metastable, then some disturbances will then take it to the more stable phase, and this is what is the rapid nucleation solid phase. So let's see if we can avoid this. So what one is doing here is taking a bottle of water, putting it in the fridge, it will cool. When it's cooling below the freezing point, it remains in the super cooled liquid state, cooled to about 10 degrees Fahrenheit. So it's still water, super cool water. But then if you make some disturbance, what he is doing is basically heating it, immediately everything becomes ice. So the ice phase at this temperature is the stable phase, the water phase is the metastable phase, and it is a small disturbance like heating with the bottle. Basically makes conversion of the water into ice. And there are, goes on for longer, but really just one more thing that is on this video, which looks interesting. Same thing, this is supercooled water, and it's being poured into this cup. And you will see the act of pouring basically causes the water to freeze into ice. That we see that just by pouring, ice is being formed and the ice will grow. So this is a demonstration of supercooling, superheating, and metastability when you have first order phase. Critical point phenomena, again as I said, is not first order, but there are strong fluctuations. So this is one video that will show strong fluctuation. So what is happening here is that there is a liquid vapor interface, and one is first heating it through the critical point. You will see that the interface will disappear as one continues to heat it through the critical point. Then it all becomes gas. In the same phase, there is no interface. It will happen in a couple of seconds. And then one is cooling down through the critical point. And as one is cooling to the critical point, you will see that eventually the interface will develop, because now below the critical point there are two separate phases, but there is large fluctuation that we'll see near the interface. Now we begin to see that interface is one. Now we cannot see here because the fluctuations are so strong. There are droplets that are scattering light so strongly that you cannot see the interface, and then you see that there are droplets going up and down. Eventually, as we continue to cool down to lower temperatures, we'll have a very defined interface. That's all. So these are some general properties of phase transitions, and we have tried to illustrate these properties just by looking at simplest kinds of phase transitions that all of you are familiar with, which is liquid solid or liquid gas, this kind of phase transitions. But of course, I mean, there are many other kinds of phase transitions that people are interested in, to observe and people try to understand in quantum standard physics. I will probably have some questions to talk about these first two, the normal superconducting transition and superconductors. I may also talk about some models for transitions between the paramagnetic phase and the magnetic order, ferromagnetic transitions, for example. Then there are liquid crystals that have many phases, and there are transitions between two adjacent phases in liquid crystals. For electricity, there are similar transitions that we see in magnetic systems. Something that is a little similar to superconductivity occurs in superfluid. If you look at helium-4 and also helium-3 and cool it down to very low temperatures, then there is a transition from normal fluid to superfluid. Many other transitions that are there. Of course, I mean, I don't really have time to talk about actually any one of these transitions in great detail. So what I'm going to do is general discussion of phase transitions is going to stop here, but I'll then introduce the second topic of this lecture, which is also very closely related to phase transitions, which is spontaneous breaking of symmetry. And one talks about symmetry breaking and phase transitions together because in many cases, in nearly all cases of phase transitions, one finds that at the phase transition point, the symmetry of the system changes. This is not 100% general in the sense that there are some phase transitions where there is no change of symmetry. We have already just mentioned the liquid to gas transition, for example, one in which there is no change of symmetry, so one can eventually go continuously from the liquid to the gas or the other way around. But if you look at the solid to liquid transition, the liquid crystalline solid transition, that is one in which there is a symmetry. And what one finds is that the low temperature ordered phase typically breaks one of the symmetries of the underlying Hamiltonian. Or the high temperature phase typically has the same symmetry as that Hamiltonian. As one, let's say, decreases temperature, one goes from there to a low temperature phase. Typically, that phase will have symmetry which is lower than the symmetry of the high temperature phase, which is essentially the same as the symmetry of the Hamiltonian. So let's just look at again this transition that we've been discussing earlier, the liquid crystalline solid transition. So I mean, if I look at a typical configuration in a liquid, atoms or molecules, they are not organized in a very regular manner. So we'll get some irregular picture like this, a snapshot. Whereas if I do that for a crystal, then you will see that things are more organized. So here, at least the usual definition of symmetry or usual notion of symmetry often leads people to think that the crystal is more symmetric than the liquid. Because I mean, the snapshot here looks more regular, whereas the snapshot here is very irregular. But that actually is not the right way to look at it. And I'll try to argue in the next few slides that the liquid actually has a higher degree of symmetry. And one of the symmetries, which is the transitional symmetry, actually is broken as one goes from the liquid to its right side. So the next two transferences are a bit technical, but nothing very something that those who have done at least high school physics they will be familiar with. So we'll be talking about two symmetries. One is the symmetry of the Hamiltonian. Hamiltonian is basically the quantity that the energy function that is about how the energy depends on the various coordinates and momenta of the system. So again, a system of particles. When you look at basically crystallization or liquid or gases, we are basically looking at a system of particles. There, the total energy has two terms. One is the kinetic energy, is squared over 2m, and then there is an interaction term. That is the potential energy, how these atoms and molecules are interacting with each other. And this interaction typically depends on the distance between the ith and the jth particle. So what one is doing here is talking about all pairs of molecules, assuming the interaction is pair interactions. And the interaction is generally true. Very few cases there are some exceptions. But the interaction depends on the distance between the two particles. And the distance between two particles is supposed to change when you transform both of them by the same amount. So if I make this transformation that the coordinate of the ith particle is changed by R0, the same is done for all the other particles, then that will keep this quantity invariant. As a result, the Hamiltonian will not change. So the Hamiltonian is invariant under uniform translation. where one is changing the coordinate of individual particles, all of them by the same amount. Instead of translation, if you look at rotation, for example, there are models in magnetism where you have the spin vectors, and the interaction is basically a dot product, scalar product of two spin vectors. Again, as you know from elementary mathematics, the dot product doesn't change when the two vectors are rotated by the same amount. So again, if you have a uniform rotation of all the spins in the system, then the Hamiltonian doesn't change. And so uniform rotation is the symmetry operation for the whole Hamiltonian. So these are the symmetries of the Hamiltonian. But what we are talking about here is the symmetry of the thermodynamic state. When there is a phase transition, what I'm trying to say is that the symmetry that you have in the high temperature state and that you have in the low temperature state, these are different. There is a change of symmetry. So what one needs to understand is how to define the symmetry of the thermodynamic state. Not individual. See, here we were looking at snapshots. And you cannot judge by looking at snapshots because thermodynamic state is not just one macroscopic state. It has a very, very large number of macroscopic states. It goes through. And basically, that is what one wants to understand. Symmetry of the thermodynamic state is basically, first of all, one has to understand how to define a thermodynamic state. Thermodynamic state is not a single macroscopic state. It is a collection, an ensemble of macroscopic states. And the system basically explores a very large number of macroscopic states. And there is a probability measure, which is basically the probability that a particular macroscopic state n offers the answer. So this Pn, this is basically something that specifies the thermodynamic state. That in a thermodynamic state, the system is exploring a very large number of macroscopic states, and the probability that a particular macroscopic state occurs in the ensemble is given by the probability measure. Now this depends on what the actual form of Pn is, it doesn't matter. Typically what one finds is that so-called canonical ensemble, where there is an external heat bath at a fixed temperature and your system is kept equilibrium with the heat bath. This depends on exponentially on the energy of that particular state. So this is something that you should keep in mind, that thermodynamic state is defined in terms of this probability is associated with the probability of occupation of individual states, and this probability depends on the energy of that state. And if I want to look at some thermodynamic average, like whatever you want, internal energy and things like that, this will be obtained by this kind of average. That you want to find out, you want to look at an average of some quantity O, internal energy. So is the Hamiltonian operator. Then you basically look at its value in a state n, multiplied by the probability of that particular state, the sum of all states. So this is just statistical mechanics in 2 minutes. Those who are not familiar, perhaps this will not really stay in your mind, but others find it something that they know. So in terms of when you talk about the symmetrical thermodynamic state, we have to look at the symmetries of this probability measure. And the question that one has to ask is that, is this probability the same for all microscopic states related to each other by a symmetry operation of Hamiltonian? Hamiltonian has some symmetry operations, and a microscopic state related to another microscopic state through one of the symmetry operations will have the same energy. Question is whether in the ensemble they will have the same probability. It would seem that that is what how things will work, because this Pn canonical ensemble depends on the energy. So all states related to each other by a symmetry operation of Hamiltonian by definition the same energy. So then it's difficult to see how this Pn can be different for the different states. But actually what happens is that when there is a spontaneous direction of symmetry, what one finds is that there are different states related to each other by symmetry, but all of them don't have the same probability. And it's this way that the thermodynamic state actually is breaking the symmetry of the Hamiltonian. So there are some operations which with the energy invariant, but the states that you get by applying this symmetry operation are not equally occupied, don't have the same probability in the measure that is used in calculating various aspects. So, and to understand this, basically one has to calculate averages, because the probability measure that goes into the calculation of averages. So if one calculates the averages of appropriate quantities, then from that one can extract some information about the probability measure. So just look at this system of particles. So here, if I want to distinguish between the symmetry of the crystalline solid and the symmetry of the liquid, one thing that can be used is to look at the local density, which is basically counting the number of particles that will be in a small volume divided by the volume of that particle. And in the liquid phase, now if I look at liquid, if I look at a glass of water, and if I look at different points in the liquid, the density of local density is going to be the same everywhere in the liquid. And this is the consequence of transitional invariance. That Hamiltonian is transitional invariant, so if I go from one point to another, by uniform transition, that doesn't change anything in the sense that the energy doesn't change. And if the state has the same symmetry as that of the Hamiltonian, then the liquid phase, and that's the liquid phase, the density has to be the same. Whereas in the crystalline phase, the average local density is not the same everywhere. It is the peak at some points are survived, and are survived on a lattice. So the point is, the liquid phase is invariant under transition by any vector. Every point in the liquid is equivalent to every other point in the liquid, apart from boundaries and things like that. Whereas in a solid, every point in the solid is not equivalent to every other point in the solid. This point is equivalent to that point, but this point is not equivalent to the point in the center. So a solid is invariant under only transitions by lattice vectors, whereas the liquid is invariant under any arbitrary transition. And in this sense, the liquid has higher degree of symmetry than the solid. So as one goes from the liquid to solid, the symmetry is reduced, and this is not spontaneous in the sense that there is no external potential that is saying that the particles have to sit there. But they choose their own positions, and one particle is stored in its position, while the other particles basically follow the lattice structure, and this is done spontaneously. This is an example of spontaneous liquid symmetry. And this happens, this is one of the characteristics of the liquid to crystalline solid transition, where this symmetry is broken. How many minutes? About 10. So similar things can be seen in many other phase transitions. For example, liquid crystals, there is a transition called the nematic to isotropic to nematic transition. Liquid crystals are rod-like molecules. In the isotropic phase, as depicted here in this cartoon, they are oriented in all possible directions, arbitrary directions. And so this has rotational symmetry, whereas in the nematic phase, they get oriented in a particular direction. Majority of them are going in a particular direction, so that has broken the rotational symmetry that was present in the phase. And again, a lot of work has been done between transitions between isotropic and nematic phase and so on. Maybe that's the main platform. I was talking about magnetic interactions, and let's look at Heisenberg magnet with this side of exchange interaction. And Hamiltonian has a global symmetry that is invariant under rotation of all the space in space. But 3 dimensions, for example, if you pull this Heisenberg magnet below a certain temperature, it will develop a spontaneous magnetization. And the direction of this magnetization basically breaks this symmetry under rotation. Hamiltonian, albeit the same, but as soon as the system has actually gotten into a phase with a non-zero magnetization, the direction of that magnetization is special, and the rotational symmetry of the system is then broken. So these are all examples of symmetry breaking arising associated with phase transitions. I just wanted to point out something that I saw a few days ago. It has nothing to do with Collinson physics, but which shows this kind of a symmetry breaking. And this maybe there is no connection, but at least at this particular level there is some connection, and it might be useful to think about it. This is basically the work that got Nobel Prize in Medicine and Biology this year. And what they are looking at is basically cells in the brain. They call it grid cells. And the mouse is basically roaming around here in a box, and the bottom of the box doesn't have any it's just flat, it's plain. There's no special point on this block. Every point is the same as the other point. So the bottom is basically invariant under translation. But what they look at is basically the firing of some neurons in the brain. And they find that this firing becomes large only when the mouse is at some special points. And the special points basically form a triangular lattice, which is the most common lattice that we have in 2 dimensions. So basically, if I look at the firing rate, look at a particular neuron, which is called this grid cell, and look at its firing rate, number of spikes it fired per amount of time, this will have peaks at special points in this two-dimensional plane. Two-dimensional plane by itself is featureless. This is like a liquid, whereas it's now gone into a representation of this bottom plane in the brain of the mouse has broken the symmetry, which says that every point on this plane is equivalent to every point. Now there are some special points. Special points actually form a lattice, which is special points picked up by that particular grid cell, where it fires much more as compared to fire somewhere else. So there is some symmetry breaking here, but of course the whole process and mechanism are very different. But this is one occasion very different from quantum physics, where you come up with this triangular lattice. It's very common in quantum physics. Okay, so going back to ordinary case. This concept of symmetry breaking, I just want to illustrate a little more of that using a model which is very common, studied by many people in statistical mechanics. And that model is called the Ising model. I think just wanted to put this picture because it shows that he's actually doing experiments. So it's a very theoretical model, but it doesn't matter. I mean, he did both theory and so basically what this model is involved is again a model of magnetism, where it is a lattice, and this lattice is generally taken to be a square lattice, a cubic lattice, or something like that. Each lattice side there is a variable, the Ising variable, which can take two values, plus 1 or minus 1. And then there is an interaction among these Ising variables, and then there is an external magnetic field also which interacts with this Ising variables. And if interaction is near its neighbor, the model becomes a simple model. Nearest neighbor Ising model, and on a lattice, and typically we'll be talking about on a square lattice. And this J is positive, which basically means that if two of the variables of the same sign, the energy is minus J, and if two variables of different sign, the energy is plus. So there is a tendency of all these variables to line up, to have the same sign. So, one finds that in two-dimensional systems, two-dimensional, three-dimensional systems, this model exhibits modeling. So, in the high-temperature space, diamagnetic space, there are more or less equal number of the up. When I draw an up arrow equals plus 1, I draw a down arrow equals minus 1. So, in this picture, we have more or less equal number of up and down spins. This is a paramagnetic, a non-magnetic space, and then low temperature, it goes into a ferromagnetic space, where these are aligned. These spin variables are aligned. And you can see here I have drawn one of these ferromagnetic space where all the spin variables are plus 1. But there is also equivalent ferromagnetic space where all the spin variables are minus 1, which is basically where I draw one down arrow. And both of these phases, one in which magnetism is positive, other case where magnetism is negative, are equally likely. But the system chooses one of them. It doesn't go from one to the other. So as one goes from high temperature is n is equal to 0 because this is essentially equal number of up and down spins. So at particular temperature, which is the critical temperature of that model, system goes into the ferromagnetic state, and depending on particular experiment that we are doing, either goes into M positive state or goes into M negative. And it never, so as soon as M becomes non-zero, the up-down symmetry is broken. This is the broken symmetry that we are talking about. It's discrete symmetry, earlier we talked about quantum symmetry, but it doesn't really make a big difference. I mentioned this model because exact solution of this model is available. Very few statistical mechanical models, non-trivial models for which exact solution is available, which is on server. And you can see that this magnetization, autoparameter, sigma average, is 0 above the temperature, and then as one goes to a temperature lower than that, then it begins to have a non-zero value. Here I have drawn a curve where it's positive, but it could equally likely have been negative. And there is no particular reason so that it will always go to M positive, but it goes to a non-zero value of M, which basically breaks the up-down symmetry, which is basically the notion that we are trying to test on. One more thing that here, the specific heat shows a divergence at the transition point. It's a continuous transition. M is 0, but it goes continuously from 0. There is no jump or anything like that. And at that point, there is a very divergence in specific heat, which is an example of large fluctuations that I was talking about in the context of continuous phase transitions. So, very quickly one minute. So we'll wrap up. I mean, as I said, I guess there will not be much talk about superconductivity here, but we are doing because of the time. Also, just maybe one thing about. So superconductivity is something that I'm sure all of you are familiar with. A transition where the resistivity goes to zero, function of temperature, and the superconducting phase exhibits many interesting properties. And about 30 years ago, high temperature superconductors were discovered, but materials in short superconductivity are much higher than temperatures much higher than those earlier superconductors. And this is an area, you can see there's a phase diagram again here. There is a volt opening and temperature. There's a phase diagram. And we have been working to understand some aspects of this phase diagram and also the behavior in the magnetic field of this high temperature superconductors. Those are related to this phase transition concept and global symmetry concept that I introduced. Just the last slide that I want to show. This is just, in some sense, in connection to what we are going to hear about in the lectures from next one today, but tomorrow for the Higgs. And here, again, this is actually from the Nobel lecture of Peter Higgs, where he talks about the work for superconductivity, which was carried out by C.W. Anderson. I had mentioned, I showed you a picture at the very beginning of the talk, that some of the concepts, etc., that were invented by Anderson, trying to understand this superconducting phase transition. Later on, helped the Higgs to solve some puzzle that was creating the Wilson theorem and eventually the Higgs mechanism. Tomorrow you'll hear about both the theory and the experimental verification, which came. So, just to conclude, I hope I have given you some idea about why phase transitions are interesting, and also some idea about symmetry, in the sense that phase transitions being very closely related to the taking of symmetries, and when you study phase transitions, you can understand what symmetry is taking of in the transition. And also, it's not just one part of physics, but all areas of physics where these concepts and ideas are important. That's pretty much all it is. Thank you.
Before we go to the next talk, I understand that those of you who are in the back are having trouble seeing the screen. So what I would request is that over the next minute, 2 minutes or so, without breaking symmetries and stuff like that, if you could just kindly, from the last rows, move up to the front, because there are enough seats in the front.